finding all of these probabilities. And we've seen some scenarios where, you know, the probability is a little more complicated than a one-step thing to calculate. Like if I was selecting 2 people from the class, and I wanted to know if the probability that they finished their homework last night. So if I wanted the probability that one person finished their homework, and I picked AJ and Josh, it could be that AJ did and Josh didn't, or Josh could have and AJ didn't, right? But if I picked, let's say, I took this whole half of the room and I wanted the probability that one person did and nobody else didn't, then it could be AJ was a yes and these other 5 people were a no, or Josh was a yes and the other 5 were no, or Blake was a yes and the other 5 were no, and I have to keep adding these together, right? And that becomes really time consuming if all of a sudden I said, okay, let's say out of the whole class, I want the probability that only one person did their homework last night. Because then I have to add together 15 different things, 15 different calculations for the one person being a yes and the 15, or the other 14 being a no. Or what if I said I want the probability that at least 3 did? Then it becomes even more complicated because I have to pick at least 3, so 3 or more, so then I have to have a few people being no and everyone else being yes. And all of a sudden, these probabilities can grow really complicated really fast. Okay, but there are some shortcuts for calculating them. So that's what we're going to look at today. The situation I was just describing is what's called a binomial. Binomial, so bi means 2. There are 2 options. You did your homework or you did not do your homework. So it's a yes or a no. To be a binomial, there has to be a fixed number of trials. So I had to be looking at 2 people or 6 people or the whole 15 people, but there's a fixed number. I'm not just going up to infinity. I had a fixed number of trials. They are independent. Okay, whether or not Corey did his homework does not impact if Anna did her homework. They are independent. They don't change each other. For each trial, like I said, binomial 2 outcomes, success or failure. The typical notation is a lowercase p for success and a lowercase q for failure. And the probability of success is the same for each. So to be binomial, we have to have these conditions satisfied. So our first one. A player rolls a fair die 10 times. The number x of 7s rolled is recorded. So, first of all, to be binomial, there has to be a fixed number of trials. Do we have a fixed number of trials?
Yes.
Yes, how many is that?
10.
So my n is 10. There are 10 trials. We're good there. Are they independent? What I roll the first time, does that change what I will roll the second time? No, so they're independent. We're good there. There have to be 2 outcomes, success and failure. Do we have those? Yeah, it's 7 or not a 7. What's the probability of success, the probability of a 7?
1 in 12.
So we have, when you roll those dice, right, to get a 7, you could have a 1 and a 6, or a 6 and a 1, 3 and 4, or 4 and 3, 5 and 2, or 2 and 5. So there are 6 options that would add up to 7. Out of how many combinations when you roll 2 dice? 36. That came up a couple times. 6 times 6. So 6 out of 36, which reduces to 1 over 6. So what would be Q, the probability of not a 7?
5 over 6.
Yeah, they're complements. So if you know P, Q is just 1 minus that. So we've met that. And is the probability of rolling a 7 the same every time you roll those dice?
Yes.
Yes. So this is a binomial. Alright, next one. An official with the FAA randomly selects airline flights until she finds 10 that were not on time. The number of flights that needs to be selected is recorded. So, first requirement, there has to be a fixed number of trials. She's just going to go until she gets 10 that were not on time. So it could have been my first 10 were not on time, Or I might have to find 20 flights or 30 flights or 40 flights or 50 flights. Do I know when she will get to stop? No. So this is not a binomial. Because we do not have a fixed number of trials. Okay, C. In a class of 30 students, 55% are female. The instructor randomly selects 4 students. The number X of females selected is recorded. So when I look at this, we have a fixed number of trials, right? We're going to select 4 people. Are they independent? So if I were taking this class, for instance, okay, when I select my first student, the probability of being female, so we have 14 students present today, and 10 of them are female, so the probability of the first one being a female would be 10 out of 14. What's the probability that the next one is a female? 9 out of 13. Are those independent then?
No.
No, because once you take that first person out, it changes the probability that the next one is female.
How do you know if they're doing it that way or just like taking 4 at one time?
Well, even so, if I take 4 at one time, when I'm finding the probability of all 4 being female, once you know the first one is female, it changes the probability that the next one is. So the only way it would be independent would be like if I'm going to draw your name out of a hat and I put your name back in and I draw again. So I could potentially select the same person multiple times. So this one is no because they are not independent. Okay. Let's look at a binomial example. So the 11 largest air carriers had an on-time percentage of 79% in May of 2008. Suppose that 4 flights are randomly selected from May 2008 and the number of on-time flights X is recorded. Construct a probability distribution for the random variable X using a tree diagram. Okay, so the probability distribution, that's when you have your X and your P of X. My X is the number of flights that were on time. We have 4 flights that we're looking at, so what are my options for X?
0.
Okay. Now, if we want to talk about the probabilities for these things, we can just calculate them. I said to use a tree diagram, that's just kind of a visual to help you. So if we're looking at the first flight, the options for that first flight are either on time or not on time, right? So, can I just call it success or failure? Success if you're on time, failure if you're not. So the first flight, we can be success or failure. Then the second flight, each of these would branch off and they could be success or failure again. Okay. Then for the third, for each of these we can have a success or a failure. And then for the fourth flight, we could have success or failure for each of those. Okay, so how many total different options do we have at the end? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 16. There's 16 different outcomes, because it's different if the first flight is on time and the other 3 are late versus the first 3 being late and the last one being on time. Okay? So, let's talk about how we define these probabilities. My number of flights here is 4. P is the probability of success. The success here is on time, so that's 0.79. Q is the probability of failure, which is being late. How would I find that?
Take
1 minus the 0.79, you get 0.21. Okay, so first option is 0 flights on time. So that's all failures. How many times does that happen? Once. Okay. And the probability of a failure is
20 or 0.21.
and so we would have that happen all 4 times. So if we do 0.21 to the 4th, we get 0.00194 approximately.
Why did you do 4 if it only had 1
I'm finding 0 flights on time. So I'm looking at the scenario where everything was failed. So it happened once, but there were 4 flights that were late. So for each one, you have to take the probability of being late. Okay.
But couldn't you say that it happened 1 out of 16 times?
Yes, but because it's not a 50-50 chance of being late or being on time, you have to think about independence. So the probability of being late and late and late and late. So you have to multiply each of those. Alright, next. If I want the probability of 1 flight being on time. So I've already used this one, that's all being failed. 1 flight being on time. So that's 3 failures, but then a success. So there's 1, I could have fail, fail, success, fail, so that's 2. I could have fail, success, fail, fail, so there's 3. We could have success, fail, success, we're doing success and then all fails, there's 4. Are there any other options where you're only on time once? Okay, so this worked out 4 times. Now, for each of those, you were late 3 times, right? So being late is 0.21, that happened 3 times, and you were on time once, 0.79. Now, I just multiply this by 4, because if you're multiplying, does it matter what order the numbers are in?
No.
So if I do 0.21 times 0.21 times 0.21 times 0.79, that's the same as 0.79 times 0.21, 0.21, 0.21. So all of those will have the same probability. We're just flipping the order. So if I multiplied this, and I get 0.02926. Alright, is this getting annoying yet?
Yeah, just a bit.
Yeah, oh, we're only looking at 4 flights. What would happen if I wanted 20 flights?
Where did you get all those numbers again from?
4 because there are 4 times it happened. The 0.21 because that's probability of being late, and you wanted 3 times you were late. And the 0.79 once because you were on time 1 time. Alright, so next, I want the probability that you are on time twice. So being on time twice. Be on time, late, late, on time, late, on time, late, on time, late, late, on time. So we've got 3 so far. You could be late, on time, late, late, on time, late, on time. Or you could be late, late, on time, on time. So 6 times would work out where you were late twice, so what's the probability of being late? And that happened twice, and you were on time twice, so that's 0.79 squared. And we get 0.16514. Alright, next, I want to do a probability that I'm on time 3 times. So I'm only going to be late once. Alright, so on time 3 times. So that could be success, 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 fail. Or success, success, fail, success. Or success, fail, success, success. Or start out late and you're on time every time after that. So that happens 4 times. Okay, so you were only late once, but you were on time 3 times. So everybody calculate this with me. You have to do your 4 times your 0.21 times your 0.79 to the third. Get 0.41415. Alright, the last option. There's only one we haven't counted yet, isn't it? It's 4 times on time. So that happens once, and you're on time every time, so 0.79 to the 4th, and you get 0.38950. How would you check that that's a probability distribution? Add up to 1. Okay, so is this how you want to do these problems moving forward? No, this was really time consuming. There are some patterns here. This one we were on time 4 times, or we were late 4 times, so we were on time none of them. This one we were late never. So look at my 0.21. We went 4, 3, 2, 1, 0. My 0.79. 0, 1, 2, 3, 4. My coefficients, we'll talk more, but we had 1, 4, 6, 4, 1. So there is a way to get this faster. That's why we are going to do the binomial distribution. So this was just kind of our motivating example. You are not going to have to do it this way. What we can do is this binomial formula. In choose x, if you remember in algebra 2 you talked about permutations and combinations. That's a combination. We're going to use our calculator to do it. That's how you got the coefficients, the 1, 4, 6, 4, 1. P to the x power, 1 minus p, that's the same thing as q to the n minus x. The exponents always have to add up to 4 because we had 4 trials. So when one of them was 0, the other one was 4. And the other one, next time it'd be 1 and 3, 2 and 2, 3 and 1, 4 and 0. They always add up to 4. This is on your formula sheet. We are on chapter 6. And so it's the bottom of that first column on your formula sheet. You just have to know what everything is. So n is the number of trials we're looking at. P is your probability of success. 1 minus p or q is your probability of failure. Okay? X is the number of successes that we want at a given time. Alright, so now we are going to practice finding these things. The one option we're going to do is on our calculator, and then we'll also talk about the table. The table I gave you does not have every possible combination, okay? Because if I put every possible probability on here, it would take forever. These are the common probabilities, so across the top you have 0.01, 0.01, 0.05, 0.1, 0.15. So if your P is one of those probabilities, then you can use the table instead of working it out on your own. But if I give you a probability that's not on this table, then we have to use our calculator to find it. Across the left-hand side, there's your N, the number of trials, and it basically just tells you these calculations. So we'll work on reading the table and doing it by hand. All right. Let's look at an example. So let's suppose 35% of all car-owning households have 3 or more cars. In a random sample of 20 car-owning households, part A, what is the probability that exactly 5 have 3 or more cars? So P, in this case, my probability of success, probability of 3 or more cars would be
0.35.
My Q, or my 1 minus P, is
0.65.
what's my N? How many trials are we looking at?
20.
20. So part A, when I say exactly 5, that means my X is 5. So grab a calculator if you don't have one. Let's first talk about how to plug it in the calculator. Can we agree that we probably wouldn't want to make a tree diagram and do all that to figure this out? Okay. So first thing you need to do, you need to start with the parentheses. Our formula, if you're looking at your formula sheet, it's N choose X. So we have 20, choose, what is my X here? 5. Then you have P, your success, to the X power. So my P is 0.35 to the 5th power because I want 5 of them that do have 3 or more. My Q, or my 1 minus P, is 0.65, and how many times does that need to happen? 15. N minus X. If I'm going to have 5 that do, then that means there are 15 that don't. So to plug this in, we do parentheses, and then you do 20. If you go hit the math button, and go over to probability, the third thing down says NCR. So we want that one. So it's 20, choose, and then we want to choose 5. Then just close that parenthesis. Then I want 0.35 to the 5th power and 0.65 to the 15th power. So I get 0.1272. Okay, let's see if we can check this on our table. So is 0.35 one of the probabilities on our table?
Yes.
Yeah, and my N was 20. So for N equals 20, you have to flip to the back of the second page. So you're looking at the 0.35 column, my N is 20, and then my X is 5. Does everybody find that number? I want to know now if you don't know how to read it on the table. So, okay. So my P is 0.35, so I'm looking in this column. My N is 20, so we have to go to the section of that table with N is 20, and my X is 5. So I want where those things meet. So I get my 0.1272, same as we did by hand. Okay? You like the table better? So the table will not always be a probability, because if I'd said the probability of P was 0.32, do we have that on the table? No. So if it's not on the table, you have to do it by hand, but if it is, you're welcome to read it off the table. So B, what's the probability that less than 4 have 3 or more cars. So if I want less than 4, that means my x could be 0 or 1 or 2 or 3, right? So we could calculate all 4 of those things, or we have the table, don't we? So could we get those 4 numbers from the table and add them together?
Yes.
All right, so let's look at our table. So we're at 0.35. We want less than 4. So that means you have to add up your 0.0002, 0.0020, 0.0100, and 0.0323. What I would ask on a test or quiz, if you are reading these from your table, please write down what you're adding together so I know where you got your numbers. I know what you put together. So if I add those 4 numbers, what do we get?
0.0445.
So that is definitely a lot faster than doing it by hand. There are some scenarios where your last decimal might be different if you did it by hand versus doing it by the table. Due to rounding error, the table is a little more exact. They keep more than 4 decimal places at a time, so if you'd done this one by hand and rounded each thing, it might be slightly different, but as long as I have the work to know how you got it, it's fine. And it will only be like the last decimal that might be different.
So if we did this one by hand, we would do the formula for 0, 1, 2, and 3.
Mhm.
Okay.
Alright, so C, what is the probability that at least 4? So at least 4 means it could be 4 or it could be 5. So how could I find that?
1 minus.
Yeah, you have 2 options. You could do 1 minus what we just found because those are complements, or you could look at your table and add up your 4 and your 5, whichever column I was in, and get it that way. So either way, we get our answer, and it is what?
0.9555.
Okay, D, what's the probability that between 3 and 5 have 3 or more cars? So that means it could be 3, 4, or 5. Yeah.
How do we know that there's only like max 5 cars?
Because it said we were, let's see. What did I talk about?
Because I thought we would go all the way up to 20.
Oh, yeah. Come on. You're right. You would add up all the way up to 20. Sorry. I don't know where I got. But the complement would be faster than adding all of those up on the table. So this one between 3 and 5, so go ahead and add those together and see what you get for me. Okay, so if we add our 3, 4, and 5,
Yeah, see, we got.
and what do we get? 0.233 what?
3.
Is that easier than making the whole tree diagram and finding every possibility and every probability that goes with that? Absolutely. Okay, so we do have definite limitations to our table because it doesn't have every possible n and every possible probability. But if we have to do it by hand, it's just a matter of using the formula and putting it in our calculator. Alright, I do want to talk about just a couple more things. I know there's not a lot of time left, but we're going to go ahead and get a couple more things down. We can find the mean and standard deviation deviation of this, if you're looking on your formula sheet, they are on there. So mean is n times p. Standard deviation is the square root of n times p times 1 minus p. Or you could think of that as the square root of n times p times q. Probably the easiest standard deviation we have ever calculated. No table involved. So I'd like to do an example of this and then I'm going to stop. Alright, so in this scenario, we're back to our car owning households. Probability of 3 or more cars, so our P is 0.35, which means our Q, or the 1 minus P, is 0.65. We have a random sample of 400 car owning households, so what is that? N. So I want the mean and standard deviation. So mean is just n times p. And we get 140. Standard deviation is the square root of n times p times 1 minus p, which is the same thing as q. And I get 9.5394. At this point, I have really taught you everything from this section. I do have a few more examples that I'm going to do on Monday, but you do technically know all of it. So I'm giving you the homework now. On Monday, we will do the last few examples. So probably the first half of class, I'll finish with examples, and then you'll have some class time to work on this. So your homework will not be due until Tuesday next week. Again, 35, it's going to ask you to interpret every probability. You don't have to do that. Make sure if I asked you that you do understand what those probabilities mean, but I'm not going to make you write a sentence on every one of them. So this